we will talk about the Karnaugh maps, which are also known as just K maps, and we will talk about how can sum of product and product of sums representation can be minimized using Karnaugh maps. So let's start about the motivation. The motivation is that this is another method of Boolean function minimization which works for for small number of variables. Okay, and then Quinn-Mikulski method, which we talked about earlier, works for a relatively large number of variables. Okay, so the procedure is that for n variables, we need a 2 to the n over 2 ceiling times 2 to the n over 2 floor rectangular grid. Okay, so n over 2. So what is the total number of cells? Total number of cells is 2 to the n, because n over 2 floor plus n over 2 ceiling, this is also always equal to n. Okay, and each cell would correspond to a unique combination of inputs, and then each pair of adjacent cells differ in only one variable. So this is like that for adjacent cell we only allow only one variable to change. Okay, so then let's talk about how do we do sum of products minimization. So the strategy is that we want to cover all ones, because we don't want to miss a one. If we miss a one, then we are talking about some other function. Okay, then blocks of one can be combined as long as the block size is an integer power of 2. So let's say block size is 2 to the k. So then this means that k variables can be eliminated by the term which represents that block. So if a block is of size 2 to the k, then we can eliminate k variables from the corresponding representative term. And each one should be covered by the largest possible block. This is self-explanatory, because if a one can be covered by a largest block, then we should use that, so that we end up with a minimal expression. And least number of blocks should be chosen because of the OR operation, because all terms corresponding to all blocks will in the end be added, because we are talking about sum of products, and each block is represented by a product of selection of literals. Okay, so for example, if a block is represented by, for example, x is equal to 0, x1 is equal to 0, x2 is equal to 1, and x3 is equal to 1, then for sum of products, what is the corresponding literal? A literal x1 bar, x2, x3. Correct? Because we take the complement when we have a complement when the variable is 0. Okay, so for product of sum minimization, we do the mirror image of this, that we always choose, we need to cover all zeros, and blocks of zeros can be combined as long as the block size is an integer power of 2, same as above, and each zero should be covered by the largest possible block, again same of the above. The least number of blocks should be chosen. This is due to the AND operation in the end. Okay, and then each block is represented by sum of a selection of literals. So for example, if a block is represented by, let's say, x1 is equal to 1, x2 is equal to 0, and x3 is equal to 1, then we have x1 bar plus x2 plus x3 bar. This is the corresponding term for that block. Why? Because we take the complement for product of sum when we have a 1. Okay, so now this is just talking. So now let's go to an example here. We do two examples, one with 3 variables and one with 2 variables. So this is the same function which we did for when we did our sum of product and product of sum representation. So let's now make a table out of it. So we say x and y here, and we say z here. Okay, so note that this is 0 and this is 1. So let's say this is 0, and then we can change one of them. So let's change y, and we can change one of them. So we can either have 1 1 or we can have 0 0. So 0 0 is already taken care of. So 1 1 and then 1 0. Okay, so this is so-called gray coding, also similar to gray coding, only we are allowing only one of them to change. Okay, so for 0 0 0 we have a 0. For 0, 0, 1 we have a 1, then we have a 1, then we have a 1, then we have a 0, then we have a 1, then we have a 0, then we have a 0. Okay, now I can make a block. So let's say I can make a block like this. So what is the term corresponding to this block? Now for this block my z is changing, but my x is 0 and my y is 0. So my term is x bar y. Correct? Then my next block is this guy and this. So this is z does not change and y does not change and x is changing. So we have y is equal to 0 and z is equal to 1. So we have y bar z. So in the end we just add. So my sum of product is this term, this expression. Okay. So now let's do the product of sum expression. So for product of sum we will have something like let's say we will have this guy, and this guy corresponds to x is equal to 1 and y is equal to 1. So we have x bar plus y bar. Okay, and then we will have another one which is this guy. Okay, for this one z is 0 and our y is 0. So we'll say y plus z. Okay, so this is my sum of product representation and this guy is my product of sum representation. Okay, so then let's do an example for 4 variables now. So for 4 variables we will have, for example, we start with this guy. We say w and x, and here we say y and z. Okay, so this is 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Okay. 0, 0, we have a 0, 0, 0, 0, 1, we have a 0, 0, 0, 1, 0, we have a 1, we have a 0, and we have a 1 here. 1, 1, 0, 0. Okay. Then we have a 0, 1, and 1, 1. And then we have a 0, 1, and then we have a 1, 0. Okay. Then let's make blocks. So now let's talk about the sum of product expressions. So for sum of products, we can have this block. And what is the block size? The block size is 2 to the 2. So which means we can eliminate 2 variables here. So now you can see that for this one, w is equal to 1 and z is equal to 1. So we end up with wz. This is the first one. Now, what is the second one? So second one may be this guy. Okay, so this guy we can eliminate one of them. So we have w is equal to 1, x is equal to 0, and y is equal to 1. So we'll say w x bar y. Okay. Now let's use this guy. Okay, so this guy is w is equal to 0, x is equal to 1, and y is equal to 0. So w is equal to 0, x is equal to 1, and y is equal to 0. Okay, now let's choose. This is the only one which is left, so we can choose this block. Okay, for this one we have y and z both equal to 1 and x is equal to 0. So x bar yz. So we say plus plus plus. So this is my minimized expression for this Karnaugh map in the sum of product representation. Okay, now let's talk about the product of sum representation. So for product of sum representation we will have Mm, let's choose this one first. So then this one is w is equal to 0, y is equal to 1, and z is equal to 0. So w is equal to 0 means w plus y bar plus z. Okay, and then let's choose now. What can we choose? Let's choose this one now. So this one is w is equal to 1 and y and z both 0. So w bar plus y plus z. Okay, so now let's choose this guy. This guy has w and x both equal to 0 and y also 0. So w plus x plus y. Okay, now let's choose. We have to choose this guy. So this guy is w0, x1 and y1. So w plus x bar plus y bar. And lastly, we have to choose this guy, which has x is equal to 1, y is equal to 1, and z is equal to 0. So x bar plus y bar plus z. Okay. So this is the sum of product expression, and this is the product of sum expression using the k maps. So note that when we did for the max term and min term expressions, this guy had 8 terms, and this guy had, I mean, it had 8 terms for the sum of product representation as well as the product of sum representations, because we have 8 min terms and 8 max terms. Okay, but this guy, now we have 5 max terms and 4 min terms here. Okay. Okay. So okay, so this is it about K-maps and the examples for 3 variables and 4 variables, both for product of sum minimization and sum of product minimization. Hope it was easy to understand, and thanks for watching. Hope you liked the video.